Morning, everyone. We're waiting for a few folks to arrive at the Fluid Numeric shop for the in-person side of the training today. We're going to wait about 5 minutes, so we should be getting started around 10:35 to 10:40. All right, welcome. Thanks for tuning in. Those of you who are joining on the live stream, we're going to go ahead and get started with today's tutorial, getting started with the RCC on Google Cloud. Let me go ahead and find myself here. Those of you who are in person, we do have training accounts for you, so you don't have to spend your own money and put down your own credit cards. If you're here, you've gotten a little slip that has your training account information, including a temporary password. That account is linked to a personal Google Cloud project for you to execute all the activities we're going to be doing today. And to get the easiest way to use these accounts is if you have Chrome or Firefox on your system, go ahead and open an incognito tab. I'll go ahead and do this on my side so you can follow along. In that incognito tab, go ahead and go to accounts.google.com. Make sure I can read that. All right. Whoops. Might take that wrong. There we go. And you'll enter in your training account information on that page. I'll go ahead and get mine started. And enter in that password that's provided for you on the slip of paper. Okay, so once you've gone through that, go ahead and hit accept on those terms and services. You'll need to create a new password for this account. Okay. And then from here, what we're going to go, we have to go ahead and sign in after you set that up. All right, now from here, where we'll be working today is on Google Cloud. So to make sure you're still in that account, you can go to console.cloud.google.com, and this should bring you to the project page set up for your project. You'll need to agree to the terms of service. Keep in mind that the billing account that's set up for this project is one provided by Fluid Numerics, so again, you're not getting billed for the activities today. Now in the top left corner next to the Google Cloud logo, you can hit select a project. You'll see your project showing up down below underneath that no organization org node. Just go ahead and click on that, and that will make sure that project's active for you for the rest of the training. Okay, so I'm going to drop that down. The documentation and the code labs that we're going to be going through today. So we have one code lab up on our Read the Docs for the Research Computing Cluster. So if you are, if you're in your browser and you're following along, you can go to researchcomputingcluster.readthedocs.io, and that will bring you to our documentation, which again I will pull up over here. So there's a lot of documentation on how to use the cluster and a lot of in-depth material that we won't be getting into today, but if you go down to the tutorials section, you'll see a tab for code labs, and we're going to start with get started with the RCC code lab today. All right. Let me go back to the slides here just to cover some basics here and tell you a little bit about what we're building today, what you'll learn how to do. So this is the basic architecture you're going to be learning how to deploy today with Terraform infrastructure as code on Google Cloud. So you'll have a login node that you'll use to access an auto-scaling cluster that has the Slurm workload manager installed on a controller instance. The Slurm workload manager is going to be the tool that you interact with to submit either batch or interactive jobs to. And in the background, that controller will manage creating and deleting ephemeral compute nodes that are only used for running the jobs that you submit to it. So this way, the only static resources you have when you're running this cluster are this login and controller. The compute nodes, again, will just be created on the fly. The other benefits of the RCC, outside of that Slurm workload manager, which really is meant to provide that familiar look and feel of an on-premise HPC cluster. It does come with the SPAC package manager pre-installed, as well as a suite of compilers, including the GNU compilers, Intel One API compilers, and the AOMP compilers from AMD's ROCm. In addition to those compilers, we do have MPI flavors that are pre-installed We really provided a flavor of MPI for each compiler, particularly because some users who are doing Fortran programming, you do need to have a compatible Fortran compiler with the MPI flavor being used there. So you have a base level stack that should get you started with most HPC and research computing applications right out of the box, and you don't have to take those hours that are typically necessary to install those packages. For those of you who do container workloads, and actually for what we're doing today, we're going to be running Docker containers on this cluster. We do provide Singularity so that you can deploy those on multi-node environments, GPU accelerated compute nodes, and those types of things. So we'll be walking through today, one, how to create these resources, how to use the SPAC package manager to bring Singularity into your path, and then how to use Singularity to run a Docker image on the cloud. So we're going to go ahead and head back to our console page. Let's actually go to that code lab. So basically, I've already covered what's in the first step here, what we're going to build. Let's go on to step number 2. We're going to deploy this research computing cluster. Now, the easiest way to get started is to use the Cloud Shell with the account that's provided. So still in that same incognito tab, you can open up that Cloud Shell, which should bring you to, there it goes down at the bottom here. Go ahead and bring that up. And you can see it still brought up that same project we were working with before. Go ahead and hit continue. Now, since this is the first time provisioning that Cloud Shell, it might take a few minutes. Now, basically, the Cloud Shell is a very lightweight Debian Linux terminal for you to work with. So we're going to do all of our work out of here. It does come with the G-Cloud SDK and Terraform and a lot of the tools pre-installed, which is why we recommend getting started here. So again, you don't have to install a lot of these applications on your local system. It really cuts down on a lot of that startup time. All right, so back in that code lab, what we're going to want to do is clone this repository. So we have an open source repository for the research computing cluster. This has all the Terraform infrastructure as code, as well as deployment manager scripts in case you want to go deployment manager route to deploy the architecture that we're going to do today. So if we go ahead and just paste that git clone command in there. So again, we're just making sure we're in the home directory with that first one, and then we'll git clone. And this will create in that home directory, if we do an ls there, the research computing cluster repository. Now, once you're inside of there, there's a handful of directories. Again, if you go underneath Marketplace, what this would bring you to is the deployment manager scripts actually for our Marketplace solution, which is, we're going to be using those same virtual machine images for the Terraform deployment. But if you wanted to use deployment manager, that's where you would go. The easiest, where we're going to start today, is underneath the TF directory. There's a handful of pre-configured deployments for you. So the RCC comes in quite a few flavors. We've got a CentOS 7, Rocky 8, Ubuntu 2004, and Debian 10 base level research computing clusters. So those are just the operating systems with SPAC, Singularity, and a lot of those packages that I was talking about before. So the compilers and the MPI flavors. Now, if you're looking for specific applications, we are working towards building out a number of solutions for running specific apps. So we do have an RCC Wharf. So if you're a weather research and forecast modeling user, we do have an RCC Wharf package. And if you're into OpenFOAM and ParaView and those kinds of more mechanical engineering style CFD codes, that's going to be underneath RCC CFD. Today, we're just looking at RCC CentOS. We're going to do some really basic deployments here. Now, there's a few different things underneath this directory for us. So again, we're working with Terraform infrastructure as code, and what this really means, when you're on-premise resources, you have to go buy hardware, you have to buy your networking cables, you have to physically make a lot of connections to create compute hardware for you to work with. Infrastructure as code, you can think of as all that stuff, the provisioning of resources. So it's a way to codify what compute nodes you want, what networking infrastructure you want, firewall rules, identity and access management permissions and roles. All those things are housed in these .tf files. And we've set up this main.tf, which is really just a template with the number of variables so that you can customize this deployment to fit your needs. All the variables are defined in this io.tf, and we provided a starting template file for concretizing those variables. Now, to make this easy, just so we don't have to really get into a lot of the details of how to write Terraform and how to use it, we have provided a make file that makes it fairly simple to work with these resources. So let's take a look at that make file. What we've done is we've tried to reduce a lot of the decisions down to just setting a handful of environment variables, a number of which are actually set for you. There's only a couple that we're going to end up needing that need to set here. So we have the RCC name, project zone, machine type, image, and the max node. Okay. What we have, so when you run Terraform, you have to first do what's called an initialization. And essentially what this is going to do is Terraform's going to look through all the scripts we have here, figure out what modules, things we need from Google, for example, or other modules we might be using. In our case, we do have some Terraform modules that are coming from SkedMD's Slurm GCP repository. And all these things are kind of pulled in and copied into our local directory so that we can make calls to the right APIs to create resources. After the initialization, you create a plan. This is just a manifest of all the resources that will be created once we actually go through the process of applying that plan. And of course, that last stage there would be the apply stage, where all the resources actually get created. So what we need to do is concretize some of these environment variables. So the first one here we're going to take care of is this Rcc project. Now, if you're in that terminal and the Cloud Shell, you'll see your project is this section right here. It's the yellow text inside those parentheses. So what we're going to want to do is export Rcc project equals, open those quotes. And if you actually just hover over the yellow text, be careful not to include those parentheses. It will automatically copy it for you, and you can paste that right in. All right, and if you want to make sure that it took, you can do an echo with a $sign, Rcc project. Okay, and it should show that project there, and I think I missed an F. So I'm going to go ahead and fix mine. There we go. All right, so that looks right. Now for the zone. So Google has a lot of data centers around the world, and when you go to create resources, you do need to tell Google where you want those placed. I'm going to pick something easy that's sort of close by to us and just stick in US West 1B. If you're more familiar with Google Cloud and have a preferred zone, you can go ahead and set that in that RCC zone. Today, let's just go ahead and use US West 1B. Okay. Now, outside of the zone, the only other thing we need to set is the name if we really want to. Now, if you looked in the make file, I'll pull that back up. The RCC name, this syntax here in the make file, the question mark equals, indicates that we're providing a default value if someone's not setting this environment variable. It's going to default to RCC demo. So, you can set it if you want. You don't have to, because it will, like I said, it will default to RCC demo. I'm going to go ahead and do it here just to show you how that's done. And now that we've got that, let's go ahead and do a Terraform init. So we'll have Terraform look through our scripts and pull all the necessary modules. You'll notice in the module list that comes in, you see we've got this Lustre GCP. In case you want to deploy your cluster with a Lustre file system, that is all possible with the RCC. Like I said before, we do have this Slurm GCP scripts that are coming in for the login controller components of this. So all those things are now in place. Now, if you were to do an ls-a, which shows everything in that directory, including hidden directories, you'll see that there's now a .terraform directory, and then there's this lock file that just protects, in case you're sharing this directory with someone else, it protects this from being someone else coming in and creating a plan on top of yours. Now, if you look in that .terraform directory, you'll be able to look through and see, those modules that come in. So you see we've got RCCTF, Lustre GCP, the Slurm cluster compute, controller, login. So it lists out all the different components of your architecture. Now the cool thing here is if you did want to modify things on the fly and really customize your deployment, you could jump straight into those modules and make those edits there. If you find something you think is valuable for the community to benefit from, you can then go and make contributions. Since all of these are hosted on GitHub, you can go ahead and make those contributions that way. It's a neat way to really dial in some of the features of your own cluster. Again, these are topics for another day. I figured it'd be helpful for you to know what's really going on. Okay, now we've got the initialization done. Let's go ahead and make a plan. Okay, this is going to take a couple minutes. So what's happening here in the make plan stage is we have set up as a precursor to this. You might have seen those said. It's going to be a lot of output. We basically do string editing on that basic.tfvars.tmpl file. And it swaps out some meta variables that we put in there to actually concretize basic.tfvars. So this guy was just created, okay? And this has all the variables that are set for your cluster at this point. Okay, so you see we've got the cluster name set in there, the project, the zone, the image that we're using for the controller, and again, by default, it's going to pull from Fluid Numeric's Rcc CentOS v3 images. We have an N1 standard 4 node for the login, and then an N1 standard 4 from the controller as well. And then we've got one partition here. You can see it's set to a C2 standard 8. These are the compute optimized Intel Cascade Lakes. And again, that's going to be deployed in US West 1B. So a couple things I did catch yesterday when I was working through this. Looks like I did get these fixed. That compute disk size does need to be a minimum of 100 gigs. So this is all looking good. So that's basically what's gone on so far is we've created a Terraform plan. You can see this other file down below, terraform.tf plan that just got created in addition to that basic.tfvars. So at this point, if we're ready to go, we can write make apply. And this will create all the resources. So it's going to take a little bit for this to happen. A lot of the background APIs need to be enabled, and then of course the resources need to be created. Now, what we're going to do next, once these resources are created, if you're at this stage and you've got this terminal output coming along, you can use that navigation menu to hop over to the Compute Engine API. I'm going to open that in another tab. Okay. And eventually what will happen here on the Compute Engine UI is that all of our resources well, at least the compute resources will show up here. In a minute, I'll show you how to take a look at the networking and the firewall rules and all those things. So we'll let this kind of run here for a second. Hit refresh. Should be seeing those come up now because it's got the controller. Yep, there we go. So now we've got the login and the controller node showing up live. Okay. In addition to that login and controller node, all right, if we go to the VPC network, so again, in that products and services menu up by the Google Cloud logo up in the top left, if you go down, it may or may not be pinned for you, but if you look underneath, sorry, there's VPC network. Here we are. Look at the VPC network. You should have the RCC demo networks in there. You see it's deployed in US West 1. If we also want to look at the firewall rules attached to that, you do have basically wide open firewall rules by default inside the network. So all the nodes can basically commute on any port with any protocol internal once you're inside the network. And then you do have a default allow SSH, which gives you TCP/22 access, which is the default for like OpenSSH and things like that. Outside of, ideally when you're doing this in production, what you want to do, because basically this is going to allow anyone to potentially do an SSH request against your server. Of course, OS login or the G-Cloud identity layers will protect that cluster from someone getting unauthorized access. But ideally, you really want to limit this. So if you have, a VPN service where you have a dedicated IP address that you can use to gate access there, you might want to think about, restricting that TCP/22 access down to just that single IP address for your VPN. Okay, so let's go back to that compute engine page. We should have a login and controller. Now, although yes, you can, let's go ahead and turn that tutorial off there. You can use the SSH buttons through the compute engine UI. What we're going to do today, we're just following the code lab, is actually log in through the terminal on the Cloud Shell. There are other ways you can use what's called OS login, which allows you to pair your SSH keys on your local system to use a third-party SSH tool to log into the cluster. But we're not going to do that today, keeping it fairly simple. All right, so in the code lab, we've done our init, we've made our plan, we've applied the plan. So now let's go ahead and try to log into that login node. So this first command is going to actually use the G-Cloud SDK to list all the instances in your project and in that specific zone that we deployed to. It's going to apply a filter to that list to only list out login nodes. And then it's just going to basically return that name in that variable. So if we just copy that first command there, that export all the way over to the end of that line, we'll go back into Cloud Shell and drop that in there. And again, just to make sure that this worked, you can run echo $ cluster login node. Okay, and you see it's got RCC demo login 0, which is what we see up in the compute engine UI as well. So that's good. Okay, let's go back into that code lab. And then we're gonna, in this case, we're gonna use G-Cloud Compute SSH. So this is gonna, in the background, manage creating an SSH key for us, attaching it to the profile for the compute node, and logging us in. For your demo project, this is perfectly fine to do. In production, you typically want to use Cloud Identity with OS login to gate access through SSH keys on specific user profiles. But we'll go ahead and use this. It might take a minute because, like I said, it's doing a few things in the background here to actually hop us into that compute node. All right. While that's doing its thing, I'll show you what we're going to do next. We're going to hop in this cluster. Once we get logged in, I'll show you how to move around with some of the very basic Slurm commands. So you can see what compute partitions are available. And then what we're going to do is pull down a publicly available Docker container image, just the Calce application, just as a demo. We're going to pull that in with Singularity. Singularity will convert that to a Singularity image file, and then we'll first go through how to do an interactive session on your compute node. There we go. So you might get prompted here. So if you want to enter a password, go ahead and enter one for your SSH key. If it looks like it's hanging, just go ahead and hit that enter button a couple times and see if you can get it to respond. Once you're in the cluster, I'll go ahead and make this a little bit bigger now. You should see this RCC Mote D down there. You can also see we've got some information about the package manager SPAC on your cluster. If you ever wanted to find any of the packages and any of the licensing that's associated with them, you can use this SPAC location -i and then give it the package name, and it'll bring all that up for you. Okay. So first thing, just to poke around, just run that sinfo command. It might still be setting up here, so we'll give that a second. Let's see. Troubleshooting is always fun here. Yeah, we'll give it a second to keep booting up. Might need another minute. Go ahead and hop back in. So I guess the first thing we really should check here is make sure that we're mounting from the controller If it's not mounted, we can try to force it with sudo mount -a. And if this isn't going to work for us, we'll hop into the controller and try to figure out what's going on here. Yeah, it might need another minute to boot. I'm going to just be patient with it. Sometimes that's all we can do. How's yours going, Guy?
I'm just finishing my apply.
Okay. Yeah, let me know if I need to slow down.
Only Deb is just making sure I knew what to set in the Terraform.
Okay, gotcha.
I'm not getting the same. I'm not like for some reason on my cloud shell, that little yellow bit isn't there.
Oh,
I just snagged my ID from the project that I have access to.
there you go.
Just to hack it in there.
Okay.
I think I need to be in the project for it to show up in yellow.
Yeah, like when you first drop in that menu there, yeah. That would do it. Alright, let's see what's going on here. Alright, I guess we're going to learn a little debugging today. So what we're going to do is grep for startup in the var log messages. See what's happening. Okay, so we're having some errors there. So I'm going to take a look at what's going on in the controller. Pull this up on another window so I can actually see what's going on here. It's hard to look on the two screens. Alright. Okay. And this is oh, looks like the service account does not have the permissions it needs. So let's try this. Okay, that's there. Nope, not Kubernetes engine. Okay, well, I'm going to try just redeploying this because it looks like I'm seeing in the startup script this Google auth exceptions transport error failed to retrieve, and it lists out the service account with the scopes that we need to get this thing running. So it might have been because we just started the Compute Engine API on the training account, so we'll give that a retry here. So I'm going to hop out of that. Whoops. We'll hop out of the login node, go back into the Cloud Shell. We're going to tear down the cluster and redeploy. So to tear down, you can just run make destroy if you're having this issue. If you're not having this issue, then just hang tight. I'll catch up to you in a second. I guess this is the equivalent of turning it off and on again. Okay, so they're coming down, and we'll give this another go here. While that's happening, I'm going to double check the APIs and services. Nope. Oh, it is, yeah, it's on. Okay, just give it a minute. Okay, so once this is done getting torn down, we'll redeploy and see if we can get that controller to boot properly. Oh, you're in the login node right now. So right here, training 2 RCC demo login. Okay. So you're in there. Yeah, you're in. Okay. Yeah. Cool. So try hitting S info and see if you run into the same.
It gave me a critical.
Yeah.
Yeah.
Yeah. This is the same garbage I'm seeing right now.
So try make destroy.
I'd log out of the login node. So just type exit and hit enter, and then make destroys. I think what's happening is like the first time the what you call it, compute engine API turns on, it takes a minute or two for the service account to register. I think it's a latency issue with how Terraform will enable the API and then create the compute engine resources.
Fun times.
Yeah, well, it's good to do this kind of debugging, I suppose. All right, so
What you're going to be able to use it for,
yeah. All right.
Everybody wants to use it.
All right, so I'm going to do another make plan once that's done, and then we'll do a make apply again. All right, I'm going to hit refresh up here, so you should be all gone. And then we'll do make apply. Give that another go.
It's still tearing everything.
Yeah, it takes a good minute there. Oh, that's way better.
Dude, thank you. That was hard. I was
Yeah.
like, is my project ID match his project ID? Is there something?
Yeah, no. But
My corrective squinting.
Yeah. That's the problem. We always need to adjust our eyes.
Yeah, fifth blur. Projector. Alright. Fingers crossed here. It said it did everything.
I'm gonna give it a minute for everything to boot now, and then go from there. All right, so we got our login and controller back. I'm gonna take a peek at the startup scripts on the controller. Startup script output. Of course, you can do this through cloud logging. You don't have to do it here on the serial port, but all right, we'll refresh, research, failed to retrieve, same issue. I'm gonna pull this off just so I can read it real quick. The service account was not found. This instance must be restarted via the Compute Engine API to restore service account access. Okay, so I'll just reboot the controller, I suppose. That's really weird.
I already hit the destroy button, so I'm going the same route as you.
Yeah. Okay. So what we're gonna do, just based on that error, this is weird. I haven't seen this one on my account, but of course doing this on the training accounts, different things are gonna happen. All right, so if we do in that triple bar menu, we'll hit reset, reset, and give that another go. Okay, we'll take another look at the It's still saying service account not found. That's really, really bizarre. Okay, I'm gonna do one more make destroy. I'm gonna restart the Compute Engine API. We're gonna do a full reset this time. Okay, once that's destroyed, turn off the Compute Engine API, turn it back on, and then try again. If this doesn't work, I'll hop over to my account and show the rest of the tutorial. Hopefully. All right, so we'll go to APIs and services. Actually, here we go. On the APIs and services page, down below, we've got Compute Engine API. Well, it's weird because it does have that service account. It is there. That's bizarre. Great. So everything's done there. We're gonna. All right. What I'm gonna try to do is from the products and services, go to APIs and services. Scroll down and hit the Compute Engine API. We're gonna disable it and then we're gonna re-enable it. Really doing a hard reset here. For some reason, the controller startup script is not able to execute properly. And the error that's coming back is it's complaining that the service account doesn't exist, which it clearly does. Okay, we'll give that a minute to enable. There we are. Let's make sure our service account is here. There he is. He is there. Currently inactive. Okay, there we go. So underneath the compute, all right. So I'll go back. I think that might be the problem. So from that APIs and service details page, you've got the Compute Engine API, you got metrics, quotas, credentials. We're going to go to credentials. That first service account there, the compute at developer.gserviceaccount.com. We need to go down on that status page there and hit enable service account. Now we're active. And I think that'll actually fix our problem here. We'll run through another make plan and make apply. And Guy will come around and show you in case.
I'm trying to catch up.
It looked like when Terraform enabled the Compute Engine API, it didn't enable it didn't mark the service account as active. Like it created the service account for the default Compute Engine service account.
It didn't enable the service account.
It didn't mark it as active. As it was showing up as inactive on my side.
But then for the Compute Engine API, I can manage it, and then from there, I can do, yeah, so you scroll down in credentials, yeah, and then that first service account, make sure it's enabled. Nice. Dude, yep, alright, that's gotta be it. Okay, I'll give it a well, I think you decided to destroy it, right?
I did, but I don't think you need to.
Okay, well, just enabled it, and I'm still getting this weird sinfo error.
Oh, no, yeah, you'll probably have to redeploy the cluster.
Oh.
Or restart. At least you can probably try just resetting the controller in login node, try to get it to reboot.
How?
So from the Compute Engine UI page,
Okay.
you can checkbox the two of them, and then the triple dot menu, there should be a reset. Oh, actually, usually Dwight that does the reset there. Fingers crossed.
Yeah. we got make destroy.
Yeah, exactly. That's we got
so
the new.
If you do a reset after creating something with Terraform, you don't have any issues with your manifest getting fucked.
No.
Okay.
No. Manifest is fine. Like if you were to delete these with the Compute Engine UI,
Then you would have.
you might run into issues. Yeah.
Okay.
Yeah. Big time.
Okay. Let's see.
All right, I'm gonna try logging in again and see what's actually. You know, I'm gonna check that controller first
It
because
sent me a disconnect to a broken pipe, so
that's good. So it did reboot.
Yeah.
So you just need to rerun that gcloud SSH. That's looking better. I'm not getting. That's looking way better. I think that was the problem.
system booting up, connection closed.
Oh, that did it.
Okay.
Cool. Well, that was fun. I'll mark that as a FAQ, and I'll add that to the code lab. Let me get the text size a little bigger here. There we go. All right. Make sure that yours is working here too.
Well, I don't. It's having issues with mine. Connection closed. Check possible causes of SSH.
Oh, it might still be. It might take a second to let an SSH server up.
Project set. Zone set. Login 0. Yeah. Should be it.
Yeah.
After I get the export from gcloud, can I continue to run gcloud compute SSH, or do I need to go through that process of pulling that information down first?
No, you should be good. Those variables are set for you. There it goes. Yeah,
Well,
it's just the open SSH server takes a second to boot.
It didn't like me. There we go.
All right, now try running sinfo. Damn it! Make destroy me. What?
Okay.
Oh, exit. Out of that login.
That helps, doesn't it?
Yeah. But that with that service account now being enabled, that should do it. Give you a moment. All right, so I'll do a quick recap for everyone who's online. If you're following on the code lab, so what happens is Terraform, when it creates the compute engine resources the first time in your project, it has to enable the compute engine API. The problem is when it enables the compute engine API, it does create the service account, the compute engine service account, but for some reason it's not marked as active. And you can fix that by going up to that triple bar menu on the top left, hitting APIs and services. If you scroll down to the enabled APIs, there's compute engine API. You can go to credentials. And if you keep scrolling down, you'll see that default compute engine service account. If you click on that fella there, you'll want to make sure that this is with that green check mark there. When you come in there, initially it's going to be like a gray checkout, and it's going to say the service account is not active. So you'll have a button to activate that service account. Now, once you do that, you do need to delete those resources we've created and recreate them with the now enabled service account, and that should resolve the issue. So I'll make sure that gets added to the code lab, so we don't run into this issue again. I'm gonna go ahead and get myself set back up here. Close out some of these extra tabs and just remind you where we're going. So at this point, I'll give everyone a few minutes to catch up here. But when you're in the cluster, you can make sure that you have compute nodes available. So this sinfo command is useful for taking a look at the status of all the compute nodes you have available. So here we just have one compute partition with C2 standard 8. So we've got 25 of those nodes. They're in this idle tilde state. So if you've used Slurm before, you might be familiar with the idle mix or reserved states. The tilde indicates it's in what's called a cloud state. So you'll notice, like in the compute engine UI, there are no compute nodes right now. But Slurm knows that when you submit a job, that these 25 nodes can be created for you to run those jobs. And you'll see when we go to run an interactive job here in a minute, it'll spin up a compute node for us. Now, if you have multiple partitions, they would also be listed down here as well. This little asterisk next to the C2 standard 8 just indicates that this is the default partition. So if you don't specify that in the command line, that's the nodes. Those are the nodes that you'll end up running on. Now, what you'll be able to use as well as your running jobs, in addition to sinfo, there's sq, which would show you the currently active jobs on your cluster, what their status is, and why they're in that particular status. But we have nothing running right now, so there's nothing special going on. Now, because we're using Singularity today, you can use we're going to load Singularity to our path with SPAC, since that's how it's installed. I think, let me actually check. I think these are actually set up to be in your default path. Yeah, actually they're not. So to get packages into your path, you can use the SPAC load command. Now, if you want to see what packages are available, you can run SPAC find. And you'll see that we've got, so right now we've got GCC 485 as a compiler with a number of packages, GCC 9.4, the number of packages in GCC 10.3, currently available. If we were to run SPAC find, you can list a specific package that you're looking for, and if it's installed, information about that version would come back to you. So here we're going to be using Singularity. Singularity, it's a similar technology to Docker, but it's made specifically for HPC environments. So if you want to run applications across multiple nodes, if you want to attach GPUs to the container, very simply, Singularity is a good go-to. You may be hearing it nowadays being referred to as Apptainer. But this is what we're going to end up using. This is what's available on the RCC for running container images. Now, the cool thing about Singularity is it does a pretty good job at allowing you to use multiple container image formats. So if you're already using Docker, you can pull those Docker images into your cluster with Singularity and run your packages that way. There's a few caveats when using Singularity. For example, if you're doing GPU programming, you have to make sure your application is compiled with the same CUDA versions inside the container as we have available on the cluster. So, for example, you take a look at NVCC version. This will tell you the version that it comes with. So right now we've got 11.5. So as long as you're using CUDA 11.5 inside the container, you should be good to go if you're doing a GPU accelerated application. And the same goes for MPI. Generally, you want to match the MPI version on the cluster with the MPI version inside the container. Again, topics for another day, but figured it'd be useful to know. So we check in here, see what we're doing, how we're doing, and in the next step here, we'll go ahead and pull down this CalSay image and do an interactive job.
Doing good? Yeah, I just went ahead and started the last one, and it's just sitting. When I use SPAC load Singularity, it just sat. So then I went in and I did SPAC pull or Singularity pull, and it's just sitting. So should I do Control C?
Wait for the SPAC load command. On the first time you use it, may take a good minute.
I think that's it, because I got a keyboard interrupt, so I'm gonna run SPAC load Singularity and just let it do its thing.
Yeah, I probably should have done that as well.
I'm just saying.
Yeah.
It's gonna take a minute to do that before we can even get the SIF down.
Yeah. The first time you run it, it sets up a whole bunch of files in your home directory and.
In applications that don't have any cursory symbols to tell you what the hell's going on. Even to change the cursor to something that
Like a little spinny dealy, yeah.
Can help. Because that one, that cursor tricks me. I don't know what it is. I don't know what it means.
Thinking.
It's just a pulse.
Heartbeat. I'm alive, I swear.
It's nice that console's as robust as it is.
Oh yeah. No, and being able just to hop straight from Cloud Shell into your supercomputing cluster and
You just don't need a fucking computer. You don't need a workstation.
no, just something that can get you a terminal. All right, so it's loaded now. So if you like, once it's loaded, you can check that it's in your path just by running like Singularity version. So this is the pre-apptainer installation. So what we're gonna do now is pull down this calc image. So when you're pulling a Docker image, you'll do Singularity pull, and then you'll just prefix it with Docker // so it knows to look on Docker Hub for the container image. Whoops. I meant to copy this guy, not the 3.7.4. There we go. It's a fairly small image, so this part actually is not too bad. You running out of power there?
It's warning me that, I mean, it said that even at 20%, it's 47 minutes. It's nothing like I'm still traumatized by Oryx.
Oh yeah, yeah. The power hogs.
10% left, and then it shut down.
Yeah. You have 50 miles to go, and then you're on the side of the road with a gas can.
Especially if the GPU is gone.
Oh yeah. Yeah.
It's gone. It just doesn't. Battery doesn't want that.
All right. Almost there. So the next slurm command we're going to look at is srun. And the srun is used for doing what's called a job step in slurm. And if you don't have an allocated resource already, it's going to run an salloc, which will, allocate a node for you and then run your job on that node. Now in this case, what we're going to do is we're gonna tell it, well, I only need one task, so this is what this minus n1 stands for, and then we're gonna open up a shell on that compute node. So we'll basically get an interactive session through srun. Well, it's taking its sweet time.
Stick with it.
Oh, the poll? Yeah. Yeah, almost there. I'm just gonna take a look, see what we got going on here. And it's working. There it goes.
Oh.
What happened?
Well, it says we run the cow save command.
Are you on a... I mean, you can do it on the login node, right?
Do I just need to
So yeah, if you wanted to, you could. If you do this, like if you do it straight on the login node, if you run Singularity Exec and then you run, looks like I misspelled latest. It should just say latest, not latest.
That's probably it.
Yeah,
That's probably
my apologies.
No, you're good. It's just copy paste.
Yep. And I think last time I did this too, there was like in addition to that cow, there was like some stuff like from Perl.
I got Perl warnings.
Yeah,
I
yeah.
still
I
got
saw that
the
too,
out.
but yeah, you got the cow down below saying hello world.
Yeah.
Cool. Yeah. Yeah, nothing's perfect in this world. How are we doing? Almost.
Man. You got tired of giving you warnings.
There it is. Creating CIF file. Now it's giving me info. All right. Finally.
It's crazy the difference.
Yeah, that is bizarre. So, all right. So what I'm gonna do now is just go ahead and get this, get a compute node up and running. So we're gonna do this srun -1, and that the other bit there, the --pty, is just to basically, if a shell script fails while we're running, it will exit. It will exit the shell script without kicking us out of the compute node if there's a non-zero exit code. So we'll run that, and it's going to take a minute because in the background, what's happening is Slurm says, all right, I've got these idle cloud nodes. I need to go basically provision one so that we can run this job that training one is asking me to do. So you can see now if you refresh your compute engine UI, that we now have RCC demo compute 00 being created. So it's going to go through the same boot process that we had for like the controller and login, right? It's going to ask Google for the node. Google's going to give it to us. It goes live. The startup script runs, which is basically mounting your home directories, the applications directories onto that compute node from the controller, and it's going to then start the Slurm daemon so that that compute node can register with the controller daemon and say, yes, I'm ready for work, and then it'll actually start work. And if you notice now, rather than being on the login node, all right, so I got training one at RCC demo login on that previous line. Now it's training one at RCC demo compute 0. Now if you run SQ while you're in here, you'll see I've got job ID 2. It's running a command bash for user training 1. We're in a run state, right? And it's telling us how long we've been using that node, and here's the node we're on. Great. So we're here, and again, you know, that thing we downloaded onto the home directories on the login node still available for us on that compute node. We do need to load Singularity to our path. Actually, let me see if it's still there, because I think the environments are supposed to be preserved when you. So if you have it loaded from the login node, that environment should be preserved when you're over there. So what we're going to do is just run this little simple Singularity Exec command. So what this does is it's going to open this image for us and run a container. So it's basically giving us access to a completely different operating system with other packages installed. This is really helpful if you're building your own applications. You can stick them in a container image with whatever environment you need and then deploy them this way on the cloud. Now, again, I did make a typo in this command, so if you're following along, the typo is actually in the name of that CIF file. It's calsay latest, not latest, plural. And then, so yeah, we're going to do Singularity Exec. We're going to use this image, and then this is the command we're going to run. It's going to run the calsay command, and it's going to pass hello world to that command. So you might see some stuff coming back from, some warnings coming back to the screen. Don't worry about that. But you can see it did run our little calsay command. So that's the basics of doing an interactive job. You know, basically, if you're doing research kind of work, interactive jobs are really helpful if you're trying to develop your workflows to figure out what resources you need, how you want to execute your jobs. But ultimately, from here, where you want to go is to start scripting your workflows, to get those under version control, and then using what are called batch jobs. So rather than kind of hopping into an interactive session, once you have a workflow that you know you want to do repeatedly, or you want to be able to share it with someone else to reproduce, you want to codify everything you've done into a script. So that's what we're going to do next. We're basically going to do the exact same thing that we did before, but we're now going to put it into a script. So if you're looking at step 4 in that code lab, what we're going to do is create a file called demo.sh. So all your scripts, they ought to be shell or Python scripts so that they can be sent into Slurm's sbatch command. You can use your favorite editor. I believe we have Nano on here, or there's Vim. I like Vim. So I'm going to open up demo.sh, and we're going to drop the same commands in there. So what all it's going to do, right, is indicate one at the top. This is a bash script. It's going to load Singularity, and it's going to run that Singularity Exec command. Now, what you could do at the top, and this is not shown in the code lab, is add what's called a batch header. So you can start to codify even the types of resources you want to work on, so that you're removing those decisions from an end user who might be using these scripts later. So the way you pass information to Slurm about the kinds of resources you want is using this pound sbatch directive in the front. And then you can do something like, let's say, for example, like if you only wanted someone to run this on a particular partition on the cluster, you could give it the partition name here. You can do the number of tasks. So it's either -n lowercase or -n tasks equals 1. You can set the standard out and the standard error with -o. So you could say calsay.out for your output, and then if there's any errors, all the errors will go to this file. So you do sbatch -e. Okay, so you can do calsay.out, calsay.error, for example. Now you can do some really detailed stuff in here too, like, okay, I've got one task, but you might want to ask Slurm to give you a certain number of resources for a task. So you could say sbatch CPUs per task equals, let's say, 2. Okay, and you could also ask for a specific amount of memory. So let's say 1 gigabyte. So you can do --memory equals 1G. There's a whole bunch of commands you can, or sbatch directives you can put in to really concretize not just what you're running, but what you're running on. How much of the resources you're going to use. This can be particularly helpful if you're trying to get into this phase of really dialing in your costs on the cloud, particularly because once you start to land on something that works for your applications, you can then go through your RCC configuration and change the compute node types to start matching your resource requirements. And so trimming back on the amount of memory you have per partition, how many cores you have per partition to fit your applications is one way to really start shaving off those costs. And the easy way to get started is just to give yourself a reasonable amount of resources on the cloud and use your sbatch header to really dial that in. And then kind of go through this iterative cycle till you're really just kind of stripping back only to what you need on the cloud. All right, so I'm going to go ahead and escape from this. We'll go ahead and write it. So now when you run this, all you have to do is run sbatch demo.sh, and all those directives should come through. Oh, I might have messed up there on the memory. Yeah, I did. I'm going to go ahead and remove that because I might be forgetting some syntax. All right, so now we've submitted job 3. So if we run SQ, so you can see it's running right away because that compute node's still available for us. All right, job ID 3. If I run again, it should be pretty much done at this point. But now if I look in my home directory, I've got calsay.error and calsay.out. Let's take a look at calsay.out. So you can cat calsay.out. And there is the same output we got before, and those warnings that we got from Perl, they should show up in our calsay.error. So that should give you the basic idea how you can, one, create your cluster, okay? How you can use that cluster to do interactive jobs to get you in a state where you can start to develop your workflows on much larger resources than you might have available on your workstation or even on these login node and controller. It's all these things I've just shown you. You can do, you can run these sort of interactive sessions on clusters of compute nodes or compute nodes with GPU accelerators attached. And the reason why I wanted to show you Singularity is to show you that if you're really getting into this idea of I've got to build my applications and they've got to run on a variety of systems, I really encourage you to think about going the containerization route, and wanted to show you again that RCC comes equipped with the tools necessary to be able to run those containers. So the last bits we're going to do is a little bit of cleanup on the cluster after you've run the job. So you'll notice that the compute node is still live, and this is a common spot that trips up a lot of new users for Slurm GCP and the RCC. The login node and controller are managed by Terraform. That compute node is managed by the controller, but it's not anything that's ever going to show up in the Terraform manifest. So if you try to tear down your whole cluster now with that compute node active, Terraform is going to fail, because the network, when it tries to destroy the network, is going to show that a compute node's still in use. So the easiest way you can tear that node down, if you're ready just to go ahead and take it down while you got compute nodes up, is you can use the scontrol command, but you'll need to be root to use it. So you can do sudo -i. The -i preserves your environment. So we're going to do scontrol update node equals rcc demo compute 00, and we're going to say state equals power down, so power _down. And this will, normally in the background, the system is configured that after 5 minutes of being idle, the node will be taken down for you. If you need to manually take it down, you can use this scontrol update command. And if you refresh on that compute engine UI, you can see now it's actually being deprovisioned for us. We're going to wait for that to actually be fully taken down, and then we'll go back into the Cloud Shell and run make destroy to tear down the login controller and the networking resources as well. So it looks like it's gone. So to exit out of that login node, just type exit and hit enter. So now we're back in our Cloud Shell. You could see that you're in your Cloud Shell up front there. Okay. And then we're just going to run make destroy to tear down the rest of our resources. So congrats, you made it all the way through. If you enjoy these tutorials, we'll be doing more of them, getting more complex over time. If you have requests for what tutorials you want to see, please subscribe to our channel, drop a comment on this video while we leave it open. But again, thanks for tuning in, and we'll see you next time.